Okay, this is our problem for today. A department store with 2 locations wants to attract new customers. The store sent each manager a box containing 50 multicolored plastic eggs. A gift certificate is to be placed into each egg. 5 certificates are for $400, 10 for $100, 10 for $50, and 25 were for $25. At each location, the first 10 customers in the store got to choose an egg containing a certificate. Explain how you would conduct a simulation to model the total value of the 10 certificates in a given way. 1 using tactiles, 1 using a random number table, 1 using a calculator. All right, as far as simulations go for the AP exam, you're not going to actually have to conduct a simulation. It's not practical given the format of the exam. But you would definitely would be fair game to be asked to design one. And if you're asked to design one, these would be the 3 ways you'd be responsible for it. Now maybe the question would specify the particular method that they want you to do, or maybe they would give you the choice. So obviously if they're telling you which method to use, then you have to follow that. If you are being given the choice, you would probably not choose random number tables. That tends to be significantly more awkward than you'd like to go. You'd be choosing one of these 2 guys here. All right, so after the simulation is run, we're going to answer 2 follow-up questions here. The manager at one location was surprised to learn that the total value of the gift certificates given out that day was $1,600. Using the results of this simulation, explain why you would think the sample provides or does not provide evidence that the total value of the gifts was unusually high. Okay. Next scenario. At the other location, the 10 customers were upset when they realized the value of their 10 gifts was only $450. Using the results of this simulation, explain why you think the sample provides or does not provide evidence that the value of the gift certificates was unusually low. All right, so here is one way that we could attack each one of these. So if we were to do this using technology, which would be the generic term for basically we'd be using the random number generator on our calculator. So what we need to do is figure out a way of letting the numbers represent the different values of the gift certificates. So we have a grand total of 50 multiple colored eggs. So it would make sense that if we use the digits from 1 to 50, that should be, or the numbers rather from 1 to 50, that should be pretty clean. Now there are 5 certificates for $400. So one thing we could do is make 1 through 5 worth of $400. There are 10 for $100. So what we can do is make the next 10 digits represent the hundreds. 10 for 50. The next 10 represent that. And then the last 25 represent this. Now, as long as we have it proportioned out properly, there's no law that would say that we would have to use 1 through 5 to represent the 400. Maybe we want 1 through 25 to represent the 25. If you're not told specifically how to organize this, it's your choice. But you want to try to make this as clean and as easy to follow for the reader as possible. And the more you try to confuse them, the less chance you have for partial credit if it's a partial credit situation. Now, whenever you're going to be doing these simulations, you have to be very, very specific in terms of what stands for what. Again, there's different ways that we could break that down. All right, now whenever we're going to be doing some kind of simulation, we need to be specific about what's going on with replacement versus not replacement, repeating versus not repeating. If we think about this, it doesn't make sense to do this as a with replacement. It's not like the first customer is going to open up the egg and then like close it back up and put it in for the next customer to pick, because then they won't have their gift certificate in order to do the shopping at the store. So the whole context of the problem makes sense that we will assume that the eggs containing the gift certificates are chosen without replacement. So after one egg is chosen, it doesn't go back in. So in terms of why that's important to this simulation here, using technology, we want to generate 10 distinct random numbers from 1 to 50 inclusive, meaning 10 different ones, meaning without replacement. Okay, we always need to be specific in terms of what we're going to be recording. We're going to calculate and record in the dot plot the total value of the 10 gift certificates awarded. If you're told how many times to run it, sometimes that is part of the instructions, then you would state how many times you're going to run this. If not, you're going to use that many, many times generic statement. All right, now we have a couple different scenarios that we're going to be examining here. So to be able to cover all possibilities, use the dot plot to calculate any relevant experimental probabilities. So whatever we need to calculate from the dot plot, we will. Okay, what if we were going to do this using random number tables? Well, one of the key differences between using technology and the random number tables is that blocking of digits. Random number tables, when you examine groups of digits, it always has to be the same number of digits in each group. So if we're going up to 50, then we have to block it by 2 digits. If we're going up to 500, we have to block it by 3 digits. If we're going into the thousands, block it by 4 digits, etc. So we can use the same basic number setup here, except for we need the 0, 1, 0, 5, 0, 6, and then everything will play out the same. Okay, when you're using a random technology, rather, you don't block the digits. This is as is. You don't put the zeros in front for the single digit numbers. Still need to make that assumption in terms of without the replacement, because that's going to tell us what we're going to do with repeaters or not repeaters. All right, using table D, got a typo, staring, starting at line 101, moving left to right, read groups of 2 digits, skipping any groups not in between 0, 1, and 50 inclusive, and any repeats, continue until 10 groups are identified. All right, table D, that's your textbook's label for a random number table. You can just use a random number table, would probably be more appropriate to the AP exam. You want to have a starting point, how you're moving, how you're grouping, what you're skipping or not skipping, and an ending point. All those things need to be addressed, not necessarily exactly as they did here, but addressed in some way so as the reader can accurately follow your instructions. All right. The calculated and record on the dot plot the total value of the 10 gift certificates awarded. Okay, again, you always have to specifically state what it is you're recording. You're going to have some kind of data table or some kind of graph or perhaps a combination of both. You have to be specific in terms of what you're going to be writing down or including in that data display. All right, now with the random number tables, we still have to say we're going to repeat the process many, many times, but how are we continuing? So we're going to continue with each trial in the random number table at the point where the last trial ended. So we want to be specific. We're not going to go back to line 101 and produce the exact same data. So the cleanest way to do this would be to just continue where you left off, and then that last line would be the same as this line. Okay, now with the tactiles, the numbers in the hat usually are going to be, or usually will be, the cleanest in terms of the easiest to write up. Now, it doesn't have to be practical. Like, for example, say, just for argument's sake, there were 5,000 eggs here. You're not going to put 5,000 numbers in a hat and draw them out in practicality, but in theory, well, yeah, you could if you had a big enough hat. So you don't have to be like bound by the fact of, well, it might not be realistic to put that many numbers in a hat. You're still allowed to do that by AP rubric. So what we're going to do is write the numbers 1 through 50 inclusive on 50 identical slips of paper. Okay, that identical part is very important because if the papers aren't the same size, then one number is more likely to be chosen than another. If a piece of paper is bigger, it's easier to pick than a smaller piece of paper. So that little tiny detail is important. We don't have to block digits. We can treat this assignment of numbers the same way we did here. We only have to block the digits for the random number tables. We're going to place the 50 slips of paper in a hat that mix thoroughly, or stir, or something, or shuffle if it's a deck of cards. That is an important detail that needs to be there for full credit. Okay, randomly choose one slip of paper, which will not be replaced. Remix thoroughly. We will assume that the eggs containing the gift certificates are chosen without replacement. Choose the second slip, remix thoroughly, etc., up until the 10 slips. Calculate and record on a dot plot the total value of the 10 gift certificates awarded, and then we're going to need to do that, those set of steps right here, many times. And then the calculating the probabilities is the same at the end. Now here, this write-up has you one slip of paper mix, one slip of paper mix. Probably don't have to do that. That's probably a little bit of random overkill. You could choose 10 slips without replacement, record those numbers, and then for the next run, put the 10 back, mix them all, etc. This is probably a little bit more than we need to do, and a little bit more than necessary for the full credit with this. Okay, I'm going to pause the video here. The next thing we're going to do is going to go through the how would we do this on a calculator, and that'll be the next part of the video. Okay, we're back here. So what we're going to do is a run through of the calculator keystrokes in order to accomplish this using technology. So what I'm going to do here, make sure it's clear, looks pretty good, is we're going to go to Math, and then we're going to bump over to the Probability menu. Oops, too far. And as far as generating random integers, the newer calculators have two options, random int and random int no repeat. Older calculators tend not to have that random int no repeat, but everybody should have this, so this is the method I'm going to be focusing on here. So I'm going to choose that. Okay, lower is the smallest number that we want to generate. Upper is the biggest number we want to generate. And equals is how many of them that we want to generate. So we're looking to generate numbers from 1 through 50, and we need 10 of them to represent the 10 eggs that are going to be given away. So get down to paste, enter, enter again, and it will give us 10 randomly generated integers from 1 through 50 inclusive. So what I'm going to do is copy them down here. So we got 40, 48, 12, 19, 1, 47, 6, 28, 43, 49. All right, now what we're going to need to do is to connect this to the context of what do they represent. Well, anything from 26 to 50 represents a $25 gift certificate. So those will probably be quicker to identify first. So let's scan through and get those. So this is a 40. That'll be a $25 gift certificate. 48 will be a $25 gift certificate. And we're looking for anything 26 or bigger. 25, 25, 25, 25. Okay. So let's take care of the other ones. 1 through 5 represent 400. So we have a $400 gift certificate. 6 through 15 is 100. So there's 100. 6 through 15, there's another 100. And then the 19 fits in the $50. category. All right, so let's see what we got here. So we have 400, 500, 600, 650, 675, 700, 725, 750, 775, 800. So for our first round of simulations here, the total gift certificates, leaked off the side there, the total amount of the gift certificates awarded will be $800. So let's do one more round. What we can do here is just hit second enter on the calculator, get that same command back again, and get 10 more random numbers. So copy that down where everybody can see this. So we have 14, 7, 3, 37, 1, 22, 16, 49, 2, 42. All right, so I kind of like that strategy I just used. I'm going to look for the numbers 26 or bigger. So there's 1, 25. There's 1, 25. There's 1, 25. All right, now we'll go through, look for the 1 through 5s. We've got two $100 winners here. And then the 6 through 15s, they're going to be 100. Oh, there's another one, 3. There were 4 $400 winners. That's an unusual event. And then 22 would be a 50. 16 would also be a 50. So we've got 400, 800, 1200, 1300, 1400, 1500 for those two. And then 1575. I might have made a mistake with that. I'm just going to go brute force on the calculator here because it didn't sound right when I was saying it out loud. So 100, 100, 400, so it's 600 plus 425 for the next two. That's 125, and 425, 1575. Okay. Etc., etc. Now, unfortunately, this is a little bit too time-consuming to run through a full-fledged class activity, especially since our class size is so small. So we're not going to do any more in terms of this. I just wanted to give you the feel of what the procedure would be. Okay, so after we had run this many, many times, doing as many as would be reasonable given the class size, we'd have to plot that. So I already have a number line that I printed out here that will include all possible values. So for our first two runs here, we got 800 and we got 1575. So we'd have to do this many, many times and get a decent dot plot. Okay, recall any graph that you draw on an AP exam, you want to make sure that your axis is scaled and labeled. Well, this is already scaled, so we'd have to give it a label. So gift certificate value would be good enough, something in context. And I guess we should be specific, it's in dollars. Graphs should also have titles. Very often, if it's just a number line graph like this, the label is the title. There wouldn't be a reason to repeat it. But if for some reason this wasn't like overly descriptive, put a title with it. But I think that that's probably good enough. All right, I'm going to pause here again for the second time and set up what we need for the next part of the video. All right, so what we got here is a dot plot which shows the results of computer-generated 200 simulations. So what we're going to use is this dot plot to wrap this problem up. So the manager at one location was surprised to learn that the total value of the gift certificates given out that day was $1,600. Using the results of this simulation, explain why you think the sample provides or does not provide evidence that the total value of the gifts was unusually high. All right, so what we need to do is find 1,600 in this graph. The scaling is not the best. I believe each of the dot sets here is 50, but let's confirm that. So that would make this 1,550. That would make this 1,600. That would make that 1,650. And then that missing space right there would be 1,700 and then 1,750. Now, it's not necessarily the exact 1,600. It's the 1,600 or results at least as extreme as this, which would mean 1,600 or more. So 1,600 or more would be that right in there. So the experimental probability of getting the results of 1,600 or more, or at least as extreme as 1,600, would be 1, 2, 3, 4, 5, 6, 7, 8. And we know that there's 200 simulations. You don't have to count 200 dots. So 8 out of 200, that's 4 out of 100, which is 4%. So the typical default cutoff is if an event has a probability of less than 5%, it's considered to be unusual. So connecting it to the context of this problem, the gift certificate total given out that day of 1,600, that's unusually high. That is a rare event. Okay. Here's the other scenario. At the other location, the 10 customers were upset when they realized the total value of their 10 gifts was only $450. Using the results of this simulation, explain why you think the sample provides or does not provide evidence that the value of the gift certificates was unusually low. All right, so we have to find 450 on this. And again, we've already determined that each one of the rows of dots there was 50. So right there, that represents 450. And if you don't trust me, you can confirm with the scaling of that, but that's how it works out. So results at least as extreme would be those guys right there. So you'd have to tally up all those dots, and I believe it turns out to be 31. Let me double check that on my other piece of paper here. Yeah, so if you add up all those dots or count them all up, it's 31 out of 200, which is 15.5%. So based on this simulation, the probability of getting results at least as extreme as 450, meaning 450 or less, is about, or not about, it is 15.5%. So 15.5%, not less than a 5%, so we don't have any evidence, or we do not have statistical evidence that this is an unusual event. There's nothing to be overly surprised about with a value of 450 or less. In contrast, you should be surprised with 1,600 or more. All right. Last part of this is, I have that typed out in terms of one way that you could write this up. All right, so our conclusion here for this part, which is $1,600 unusually high? So based on this simulation, the experimental probability of 1,600 or more is 8 out of 200, which is 4%. Okay, you want to be specific in terms of this probability is based on this simulation. It's an experimental probability. You probably don't have to have, based on this simulation and experimental probability, the rubric would probably allow you to one or the other. But you have to be specific in terms of this is not a theoretical probability. All right. Now, what are we going to do with that? We want to compare it to 5%. That's our typical cutoff. An event is typically considered to be unusual, but has a probability of less than 5%. Now remember, whenever you're doing comparisons on any AP free response, whether it's simulation related or not, you always have to be specific in your comparisons. 4% is less than 5%. So since 4% is less than 5%, this simulation provides evidence that a total gift certificate value of $1,600 is unusually high. Now there are plenty of other things that you could do in terms of writing this up that would probably get you full credit on an AP rubric, but this is definitely a decent, pretty efficient way of getting the job done. Okay, the write-up for is 450 unusually low. So based on the simulation, the experimental probability of 450 or less is 31 out of 200, which is 15.5%. An event is typically considered to be unusual if it has a probability of less than 5%. Since 15.5% is not less than 5%, this simulation does not provide evidence that a total gift certificate value of 450 is unusually low. Okay, I want to do a time check to see where we're at for the total amount of time in this video. If we're already close to the full period, we're just going to end it right here. I'm going to take a peek and see if there's time to talk about a couple other issues, so the video may continue from here or not, to be determined. Okay, one last idea to wrap this up here. Could we have done this without a simulation based on theoretical probability? Now, we spent the better part of at least 2 chapters talking about some probability rules. Could we have done this using those rules? Well, if we were only choosing one egg, we definitely could do it. We know the possibilities are 400, 150, and 25 as far as gift certificate values. If you calculate the individual probabilities based on a proportional breakdown, these guys right here, so we could put these in L1 in our calculator, put these in L2 in our calculator, run a one variable statistics with L1 being the list and then L2 being the frequency, and we could get the mean and standard deviation for choosing one egg. So the expected value of one pick of the egg is 8250 with a standard deviation of 109.53. Now, if we were doing this with replacement, where the first egg went back and the probabilities were the same for the choice of the second egg, etc., then we learned stuff in chapters 4 and 5 where we'd be able to figure out the mean and the standard deviation of the entire distribution for all 10 eggs. The fact that it's without replacement puts this out of what we can do by hand. That is simply too much to be done with the tools and the technology available to us. So last thought to wrap up this would be based on what we know in this class, and this being run under the assumption of we're doing without replacement, our only way to determine these probabilities would be by a simulation. If we were to modify this with it being a with replacement, then we could do our combining random variable stuff in order to get some theoretical probabilities. All right, that definitely wraps this up. This simulation can be considered complete.